Thanks, Julie and DT and everyone for organizing. I think this is a great seminar series. I had a wonderful experience as an Alvarez Fellow, and I always wanted to, I know some of you, but not all of you. And of course, there are others tuning in. And so I hope to be able to share some of the more recent stuff that I'm excited about. And what I've been doing since I left as an Alvarez Fellow. So this isn't, a review talk of everything I've done, pretty much a more recent thing that I've been very interested in and has kind of changed my mind about some of the ways one even does science. And so I tried to customize this talk a little bit towards a slightly more general audience than normal, not meaning like totally general, but it kind of will grow steadily in complexity from intro to philosophy to a little bit more technical. So hopefully there's a little bit of something for everyone, though, with a smaller group. Well, I can't see the participants list on this setting, but if it is a smaller group and you prefer to kind of go off on a tangent or talk about something more specifically that I'm talking about, feel free to interrupt me and say, we've all lost the thread, but we're interested in this, and I'm happy to accommodate. So yeah, but generally speaking, I'm going to talk about 2 to 3 recent things I've been working on, which were kind of considering what quantum computer science teaches us about chemistry and maybe science more general, and what these quantum computers might do to help us in certain tasks that are maybe not the standard ones that you hear about. How do they show us things about our universe that might otherwise be invisible to us? And so just to kind of give a very intro slide. So you've heard quantum computing this, quantum computing that in the last few years, I'm sure. And you're probably wondering at least a little bit what that's about. I'm not going to give a full, perhaps, but just overview of what we mean when we say quantum computers, because there's to some extent a lot of marketing out there. You might see Duracell quantum batteries, you might see, Samsung's quantum TV, and maybe that one's a little bit more fair based on quantum dots and things like that. But basically, I'm just going to give a rough comparison, which is to say we have this world of, you'll hear me say classical a lot, and often what I mean by that is not quantum, which is, a normal world we tend to live in. If you throw bean bags through these 2 holes, you sort of expect it to go through one hole or the other. And this is in contrast to systems which we view as quantum, which have a little bit more interesting effects to them. So if you were to do the same game and throw a bean bag through these 2 holes in a quantum system, you might find that they interfere with each other. And this is kind of the very loose definition that I'm going to use, that a quantum system, as in contrast to when I refer to a classical one, and this can be a bit confusing because you might say all systems are in principle governed by these rules of physics. But what I really mean is a physical system operated in a regime where we actually need effects like discrete energy levels and interference to accurately describe it. And we're going to, in particular, use those effects to try to write down algorithms or operations that it would be very, very hard to do without those operations. And that's sort of what we're hoping to do when we build a quantum computer, is harness those extra physical effects for some kind of advantage on a task we care about. And you might say, okay, well, what's kind of the application areas you're broadly interested in, and what's the benefit if you're wildly successful here? And a lot of people have talked about, say, optimization. So discrete optimization problems were some of the more early interests that people had, say, in annealing type situations, or whether they be discrete or continuous. I've worked a lot on quantum simulation, which is something like, given the atoms and molecules in a system, I'd like to simulate some effect that's happening, moving forward in time, or maybe what's going on inside the nucleus of atoms and atoms or something like this. And what do we hope to do? And one thing I like to emphasize is that the advantage we're looking for in some of these problems isn't just, say, an advantage you might expect through additional parallelism or faster clock speed. We're actually trying to change the scaling of the best solution of some problems. So in some cases, we might see something like, you'll often hear it termed in the field as, say, quadratic or polynomial speedups. And this can give you an advantage, just kind of picking some problem sizes and sweeping some constant factors under the rug. There are conceivably problems you could change from like a year runtime to 2 weeks. These are things like optimization of unstructured problems, Grover search, et cetera. But the ones that really, got people out of bed in the morning and made them start wanting to work on quantum computing a lot were cases where we found exponential speedups. And it's important to clarify, we don't have those for every problem. In fact, there are some problems for which we think there is no speedup. But for ones like certain quantum simulation problems and factoring of large numbers that threatens encryption on the internet, we do suspect there are exponential speedups compared to the best classical algorithms. And what this means is you can really take problems that would have taken like 10 to the 82 years and move them down to a runtime of like 300 seconds. And just to kind of calibrate you, Wikipedia tells me that the age of the universe is something like 14 times 10 to the 9 years. So really you're taking something that's impossible and turning it into a calculation that's relatively routine. And so that's the broad strokes goal of what we hope a quantum computer will add to us. And I'm going to take actually a little bit of a different tack today. I'm not going to take the purely the grass is always greener approach, which is to say you'll often hear this story if you kind of follow the cartoons at the bottom, that for the purpose of simulating chemistry or some other interesting quantum system, we sort of digitize a molecule. I've just depicted benzene here. You plug it into your quantum computer, and out the other side comes some kind of solar punk utopia where you get massive speed ups, solar cells are being designed on their own, et cetera, et cetera. And we wanted to take a different tack and say, well, what do we actually learn about chemistry from even the study of theoretical quantum computer science, both about its potential and its limitations? And what does that tell us about chemistry overall, even if we never manage to build a quantum computer? I think we will, but I think it's kind of an informative and a kind of different take on what it means to study quantum computer science. And so before I go there deeply into quantum, what do I mean by simulating chemistry? So a lot of people here probably aren't chemists or have not attempted this kind of problem. And I'm only even going to talk about a particular subset of chemistry. There's, of course, many other parts that are quite interesting. And what I will often refer to in electronic structure is, for example, I gave you some idea of a configuration of atoms and molecules, nuclei positions. Maybe I measured them in a device. Maybe I guessed what they might be, and I want to learn the properties of that configuration of a protein or atomic system. And from my calculations, I'd like to gain some amount of understanding, like how something absorbs light, how it complexes with different molecular species, or maybe how different molecules tend to interact with the surface. And the hope is that I take that understanding and bootstrap it into some level of actual control. Like if I know why things absorb light, maybe I know how to control them and design new photovoltaics. If I know why things complex, maybe I can prevent the misfolding of proteins that cause disease, or perhaps I can design new catalytic converters. But already, things that you're seeing on this slide are more than just, say, calculations. I've actually gone out and looked for something specifically rather than just run forward in time. And I want to contrast this to what simulating chemistry might be like without, say, the last 100 years of theoretical chemistry. And so what do I mean by that? Imagine that you're just given some small set of molecules that you went out and bought on the internet. You're mixing in a jar. Maybe you're just mixing drain cleaner and stuff under your sink, and you're given a ton of these reagents, and you get to mix them in any order that you want. And you have ample supply that it doesn't really matter. You're not really limited. And there's some set of output products that you want to get, some desired features of them or a specific molecule that you're interested in. And you might ask yourself questions like, how long does this typically take, or even does this happen at all? And so without knowledge of any theoretical chemistry, but if I just give you, say, the basic physical laws these molecules and atoms obey, you might be tempted to say, take their equations of motion, either in like a classical world for an MD type operation, or in a quantum world where you sort of evolve the full wave function as accurately as possible. But if you're in this situation, basically all you can do is maybe realize a handful of realizations of this, run it, and because you don't know anything about chemistry or physics, you just wait and wait and wait. And then if a reaction perhaps takes hours or days or weeks, like resting, you might not see any instances of it occur, but can you really say anything about that? And you're like, oh, well, that's a little bit concerning. I guess I wouldn't probably learn a whole lot about this particular question. And then you say, okay, wait, I heard about this thing called quantum computing, supposed to make everything exponentially faster, right? So I can perhaps utilize that to kind of get around this problem. And, we typically set these problems up as I gave you again, this molecular structure, and maybe there's some, excitation on one side of it, like I hit it with a laser pulse. And I just want to evolve this thing forward in time and keep watching and watching and watching and seeing if some event happens. And this is a rapidly developing field. I'm not going to go into too many details, but basically numerically exact evolutions to this are available often in sublinear number of basis functions. The scaling is very good. And you can contrast this to doing the exact classical competition that hits an exponential wall. And so you're like, okay, here we go. Here's my exponential speed up. I'm not going to be limited by this crutch of not being able to simply watch reactions happen anymore. Who needed that theoretical chemistry business? But one of the things that we've learned in the time that we're working on quantum simulation, long before we actually have the computers, is we can actually start to look at the universe itself and say, if I suspect the universe is obeying quantum mechanics, to some extent, it must either be or be very similar to a quantum computer, and what can I prove about such a computer? And one of the more basic things that you can kind of caricature a little bit is this no fast forwarding theorem that was proven in quantum computer science, which basically says that the simulation time of any physical process is at least a constant times the physical time it would take in the world if you do the simulation accurately enough. And the easy way to see that is if nature is a quantum computer and could simulate itself faster than a constant of 1, it could simply kind of recurse on that system and do any computation instantaneously. And so if you look at this and you say, well, the physical time needs to be longer than that, typically I have some huge prefactor of overhead and encoding, and a chemical reaction like rusting takes 10 to the 23 parallel realizations, maybe a month to have an appreciable number of them, then there's simply no hope at doing chemistry. So why don't I just give up even with a quantum computer? And any chemist in the audience or anyone who's touched a different area of science, it's like, well, of course we don't do things that way. That would be ridiculous. And that's kind of building towards the case that I'm going to make, that in fact, having a little bit of data can change problem complexities quite a bit. And so let's pivot back a second to what people often will actually do. So if you're in any of these talks on quantum computing, you'll often see these equations written up. So if you're not familiar with bracket notation, anything in this kind of angled bracket's a vector. So this is just a linear eigenvalue problem. And basically the tagline is that this equation is sufficient to describe all of the chemistry that we're interested in. It's just much too hard to solve on a classical computer because the state size of this space is exponentially large, which is the natural space that quantum computers occupy. And so we hope that we can study problems in this space and learn what we have. And so just to contrast for a second, why am I now talking about an eigenvalue problem, whereas I had a time dynamics equation before? Don't these contain roughly the same information? In particular, both of them are taking Hamiltonians as input. In one case, I give it an initial state. In another case, I'm just looking for eigenstates. And yet people have studied these in the context of quantum computing, and we often think of the dynamics problem as easier to some extent, given an initial state, and this ground state problem to be a much harder problem. So how does that connect to what I just previously said? When in fact the left one, which I'm talking about as easy, is limited to physical timescales. So if I want to know something about rusting and I'm simulating in enough details, there's nothing I can do unless I start throwing parts of my simulation away. And in this case, we're talking about stationary states. But what we've included is information, why this is often more predictive of what we care about. So we can kind of look around and say, well, the world isn't actively on fire. In fact, there seems to be this thing like energy where at moderate temperatures or moderate conditions, low energies are preferred. And because this is the case, I can seek out stationary states that are often predictive of longer time behavior. Technically, when I look at thermodynamics, it's infinite time, but yet it's often predictive of a time much, much greater than one that I actually care about. And so this allows me to make these longer predictions, and this uses this information from the world that wouldn't necessarily be available to me had I never existed in any physical world. For all I know, energy is not really a preferred basis. It could just be anything, could mix anywhere. And of course, the complexities at the top link them together. So just to give you a flavor, BQP is like P, and QMA is kind of like NP hard or NP. And so basically it says in the worst possible case, I would have to enumerate every state. But in many physical cases, thermodynamics is telling me something interesting. And this is kind of a reference back to, if we view the universe as a quantum computer, when can we have these cases of understanding when dynamics can be predicted on very long time scales by these brilliant observations that thermodynamics is obeyed. And so you might take a look at that and say, okay, well, we've used this information from the physical world, and we have these concepts like energies or free energies that let me make these interesting predictions at long time scales and reduce models. So can all physically interesting questions be answered by some reduced model? Like a small calculation, I compare two energies, I conclude this one's going to be the relevant one. And interestingly, it's been kind of a hot topic in quantum computer science recently to show something to the contrary, which is if I look at problems like, does a system ever thermalize? So in particular, if I just tile some molecule off to infinity, does it tend to reach a ground state or a thermal state? Does a system have an electronic gap? Or, will molecule X, like I asked before, say synthesizability, ever form from constituents Y? And it was actually proven that these problems are undecidable. And so this is kind of an even harder class of problems. Famous Turing halting problem fits in this class, but I'll take it to a more physical interpretation, which I'm borrowing from Chris Moore, with the citation here at the bottom, which is basically, as a system evolves in time, there are sudden qualitative changes that cannot be predicted in any way except evolving forward in time and seeing if it happens. And that no answer in finite time can ever be promised to indicate that it will never happen. So I'll give you some examples in a minute, and I'll kind of tell you why I'm taking this perspective later. But you might argue, of course, if you know a little bit about these types of problems, like how can a problem be undecidable, it often leans on the fact that the system can be in an infinite number of states. And so, for example, the problem of synthesis, I can borrow from many, many reagents and create many different molecules. And you might say, but I think the universe is finite, so shouldn't this always just be exponential time? And I'm going to borrow a quote by George Box. It basically says, all models are wrong, but some are useful. And basically, I'm going to argue that taking this undecidable perspective is actually useful in a way. And the comparison is between, if I'm asking a question like, can I ever make these molecules from these? I might be tempted to do something like, for example, take all these possible combinations. I set a maximum number of atoms in my system, and I conjecture that I'll be able to examine all the transition states in different configurations and figure out when the free energy paths are preferred and things like that. But what if I accidentally miss or don't include enough molecules? This often happens in, say, protein synthesis, where a much larger non-intuitive protein could have catalyzed a pathway that you never predicted. And this is kind of this undecidable or open picture where you might borrow from the environment. And I'm going to argue that here a data model is perhaps more predictive. And it'll be more clear in a few slides what I mean by that. But I think this is a nicer model for a problem like synthesizability, because real systems have these side reactions which can kind of trap parts of your system that can never get out, or even kinetic transport, like something explodes in your system and reagents just fly off in the universe, or these very complex autocatalytic chaotic systems where you really need more and more molecules to process them. And I'll just give you a few examples of where we sometimes see this in, say physics, which is, chemistry is often finite, but in physics, a nice simplification is taking large system sizes to see that you converge to some well-behaved limit. And if you were to lean on thermodynamics too directly without ever looking into your physical world, you might see something like a ferromagnet, where if you did the thermodynamics and took the temperature down to 0, you see that the up state is no more preferred than the down state. But in practice, any tiny perturbation tends to lock it into one or the other. You have this kind of phase ferromagnetic locking. And then to avoid the fact just saying that, well, thermodynamics didn't really work anymore, you give it a fancy name like spontaneous symmetry breaking, which says that, it's obeying a thermodynamics within its given phases. And then if you reach a more complex system where this happens over and over again in many different hard to identify configurations, you define a local thermodynamics in each one that's called the Gibbs measure. And so what's you're kind of doing is patching over this problem that there's not a single number you can take on a finite chunk, that's easy to make very predictive, and you're instead kind of redoing it in local neighborhoods. And this is kind of a hint of this problem. And if I can go off the rails a little bit to make the talk a little bit more memorable, I think you can see evidence of this in many of emergent phenomenon. So if you take, for example, the base chemicals that we see in organic reactions, you replicate them over and over again, you might eventually get proteins and then DNA, and then something like an animal cell. And for example, you see dinosaurs on Earth, and you ask, is there any computation I could have done on a dinosaur that would have told me that after a meteor, human complex life would have emerged? And I would say that that's these kind of phenomenons, these jumps from DNA to cells to very complex life, is kind of very similar or analogous to this idea of undecidability, that there was no way to say this life would have emerged except to plot forward in time, see that it did, and once you have that evidence, you can kind of use that evidence to reason about the systems now that exist. And so why am I harping on this so much? This seems like a very depressing point of view. You keep saying never predict and words like this. And I would actually say that the nice part of this is that undecidability can be formally broken by something called advice, which involves a pre-infinite time pre-computation. And the point that we're going to make is that data, including data from experiments or the real world or observations you make to make these physical models, is actually a restricted form of this advice. And so if I even just take another chemical example, if there are chemists in the audience, this question of often, you do screening of molecules or atomic systems looking for new candidates of things. And it's a pretty big open question that once you're given a candidate system, can you actually make it or not? We often lean on organic chemists and their intuition to say, yeah, I could probably make that, or I probably couldn't make that. And basically, this field of natural product synthesis is a nice example where the goal is to take things that have been made in nature, so you have evidence that it can be made by something, and then try to build on that success to go towards a target is possible and often useful as well. And so what does this have to do with quantum computing? So I talked about the complexity theory results and how if you view the universe as a quantum computer, you can take some of these proofs and statements more literally about what might happen in nature. But tying it back a little bit now to quantum computing, we often talk about problems that we would like an advantage on. And this might be, say, Shor's factoring algorithm or simulating nuclear physics. And I would say there's one class of problems that are computationally limited. So that is the input is fairly simple, but the known classical algorithm takes a really, really long time. Whereas a known quantum algorithm, often discovered by serendipity, is expected to take not so much time. But at least in principle, once I've been given this information, there is a classical, if incredibly inefficient way to compute it. And this is what often causes us to have to compete with supercomputers and like this dividing line of where approximations fail, et cetera, et cetera. But there's another type of problem, which are actually data limited problems. So you can frame these in a lot of ways. You might call it query complexity. You might call it the amount of data you collect from a physical system. But these problems are limited by the availability of data. And in this case, there's no amount of computation, if you don't have enough data, can overcome this gap. And this is kind of going to be the focus here, which is to say quantum computers often allow us to process data that come from natural systems that are quantum in using far fewer queries or collection of data events than classical. So in a case where data is provided very slowly, you might find a huge advantage even at a small number of qubits. And one of the reasons we cared so much about this is that we started to find evidence and eventually proof that I'll talk about in a second of problems that have known inputs and outputs where having a few pieces of data at each system size can actually fundamentally change the complexity of the problem. And so it's important then to realize when data can change this and when it can change your approach, whether it be measured from experiment or measured from a different quantum computer. And so let's give a motivating example for data-assisted problems. And I'll try to just tell you intuitively what each equation means, just in case you're not as familiar with the notation that I'm using in this slide. But say you're given some quantum circuit, which is just a program for a quantum computer based on small operations, and some input. So just keep in mind some like p-dimensional input. It's just going to be a feature vector for a learning problem that I put in an amplitude encoding. And my task will be to compute some output that depends on the circuit and some choice of a measurement that I do. But you can just think of this as running some quantum program forward and doing a measurement. I can code anything I want into this, and I'm going to let that circuit be as long as it wants. So it could be exponentially long in my inputs, be a very, very hard computation. And you've heard quantum computers are already good, so this clearly must be a very hard computation, right? Even if P was 1, this could be as hard as Shor's factoring algorithm or something much, much harder than that. Now, though, I'm going to give it a few example pieces of data. So rather than just giving you a raw input and saying, compute for me, I'm going to give you a few examples, call them training examples, where someone else has done the computation and given you these as additional information. And now I'm going to write out this task in a little more detail. And I'm just going to rewrite some things, and I'm going to lump the complexity of this huge circuit into this matrix BKL. And I notice that this matrix that defines my whole output of my problem is only, quadratically sized in this input dimension P. And so basically, this is at most a quadratic function of xi with p squared coefficients. So I'm going to need, in kind of a statistical learning sense, about that many data points to learn it to some bounded precision and probability. And so the punchline of this is that this was a problem, a little bit contrived for the purposes of pedagogy, where no data was an arbitrarily hard quantum circuit, as hard as it could possibly be. And with data, this was basically a trivial learning task. And so you're, okay, well, this is because you contrived the inputs a little bit, this amplitude encoding. But this was our starting point where we tried to flesh out when this actually happens. And we sort of showed that as a subclass of advice, having data that's potentially produced by, say, a quantum process can, in fact, change the complexity of your problem. So in practice, this means there's some subset of problems where having a small amount of data for each size of your problem up to some precision can effectively replace the quantum computer. And so for us, that was, of course, both super interesting and somewhat concerning. And you might ask, well, what kinds of problems are learnable from a little data? And some of our co-authors went off and wrote a paper after this that showed that basically certain ground state problems and predicting phases of quantum matter might actually fall into this easy class, where if I gave you a few examples or you had some from nearby problems that were easy to solve, then in fact, you can achieve these bounded errors. And you say, okay, well, what does that mean? Does it mean that the fate of quantum computers is to provide training data for classical models? So that would be a very practical way to use them and perhaps very useful, but it would also be a bit depressing if that was sort of the primary use, was to just create tables that later models could lean on for one of the most interesting and kind of exciting fringe technologies that we're developing today. And so what we aim to do is basically to narrow down examples where this wasn't the case, where there's really no way that doing solely classical processing can kind of change the game for you. And so the setup that we considered is now one a little bit closer to physical experiments. So imagine that you're out there and you have some molecules you're interested in. Maybe you're looking at black holes or physics, or you have another quantum device doing a simulation for you. And this is not so different even from situations that are in the lab today. Maybe you're probing some particular dye that you have in there, and you're getting back and forth what you'd call conventional experiments, which is I put a probe in, I do a classical measurement of that probe. It gives me like, a voltage back or an intensity back, and I collect this information. And I'm going to contrast this to a situation where I'm allowed to say, collect that probe state, and then wait just a little bit longer and collect one more probe state and do a bit of a joint measurement on the two of them. And so the two scenarios are going to be that I'm some classical learner or operator. This is kind of like lab experiments are today. I'm operating a laser apparatus and writing down my amplitudes, or rather my computer is, of some experiment that I do. And each time the state comes in, I measure, get out some signature of it, and repeat. And I contrast this with the top situation, where I'm allowed to keep around one of these states for a little while longer before I do my measurement and keep them in memory. And I want to contrast these two situations to say, how many experiments or repetitions do I need to do in order to learn something about my state that I'm interested in? And I'll also examine the case where it's not just something about a state, but rather I can take probe, expose it to a process, and learn about some process as well. And so in this work, basically, we built on some previous work by our co-authors to show that this advantage could be boiled down to an incredibly simple task that required only 2 copies, and we could have an exponential difference in the amount of data that we collected. So keep in mind that exponential difference from early on, where it was the difference between, collecting data for thousands of years or doing it in a few seconds. And basically, we have proofs of this separation, and then we wanted to say, well, does it work when there's noise? And so we ran it in a real experiment as well. So a big part of this work was asking, what's the simplest task we can have an advantage on? Because a goal of ours was to understand where these separations come from and sort of, can we get it on a real quantum device? And does that, how do we do these measurements, basically? And so this is going to get a little more quantum notation-y, but again, I'm going to try to bridge it back to just intuitive explanations of what you're looking at, and hopefully it won't be too hard to follow. So my setup is going to be, I'm given n copies of this unknown state. So this is many times I put a probe next to a molecule, I take it back. I put a different probe next to a molecule, I take it back. And the form of my state is going to be a very particular form of state, which is as simple as I could manage to make it, which is this I plus alpha polyoperator state. And what's going to be allowed to be known is the form of this state, but the exact P and the exact alpha will be unknown. And the important features of this state is actually unentangled. So it's a classical probability distribution over states, but it's in different non-commuting bases. And so I can realize this with a depth 1 circuit that's quite easy. And this is just about the simplest kind of probabilistic mixture that I can build. And if you were to write this out because of the tensor product, it would of course be exponentially large, but it has a fairly simple classical description as well. And I'm going to contrast these 2 scenarios where someone gets out copies of rho, this state that I get in, and they can do anything they want to it, but then they have to destructively measure it, versus the ability to keep around 2 at once before measuring it. And so this task is take any measurement you want on n copies under the constraints of conventional or quantum enhanced, collect some classical data signature of the state, and then given a new operator, give me the expected value. So once all of the measurements are complete, I give you a new challenge operator, you tell me its value. And alternatively, I can give you 2 and ask you to say which one is bigger. And so a large part of this work was actually showing that once we made this problem simpler and simpler and simpler, that it was still in fact hard for any classical or conventional adversary that can do arbitrary experiments to my system. And the summary is that, yes, this task is quite hard. You need an exponential number of copies to do what I just said if you're only measuring 1 at a time. Quick sketch of the proof technique is that you reduce it to a discrimination task. And the reason we chose the state form we did was we could do these integrations sort of by hand and show that even adaptive strategies with kind of arbitrary computation time can't do anything to resolve the ambiguities between them. On the other hand, the quantum experiment is actually quite straightforward. So basically, this is just a quantum circuit diagram that I have over here. You can sort of read it left to right like music notation. These are just known operations we know how to do. And this is these unknown states coming in, multiple copies of them. And these are just classical bits that I read out. And so basically, we're going to run 2 n rounds of these things and just collect a handful of classical bits by doing joint measurements. And the punchline is that rather than that exponential before, I'm going to need a constant that has a small dependence on the precision that I want to know this value to. I'll just skip over the middle part that says we know a formula by hand that's relatively simple to get from A to B, but that won't be the most interesting part. So summarizing quickly the scale of separation. So I'm given many copies of this sensor state or something that you want. You take any copies, measurements you want, collect some signature, given a new poly operator, tell me something about it. And I'll contrast this quantum and classical scenario. And basically the conventional scenario, exponential, the quantum scenario, very easy, basically. Straightforward, compute is efficient, sampling is efficient. The classical case is just a nightmare. And one thing that we were very interested in this, because I promised you something about learning from your environment, not just kind of rote computation, was that once we have these sketches, you can ask, did I sort of need to know the right answer? Or was this something that if I took in states in nature, could I actually discover something using this process? Or said in the language of machine learning, can I use this as a feature of a quantum state to learn these types of tasks? And this is also important because if you compare to an adversary that can learn, you might expect some kind of weird fluctuation in the noise could reveal your state and be a bit different. And we're actually going to look at both a supervised setting and show that we can train on very small sizes. We use the recurrent networks, we could go much larger, and unsupervised, where I'm just kind of using a caricature picture for here until 1 or 2 slides for now. And I think it's important to imagine, I've talked a lot about a setup where it's a little bit contrived. So we're going to build these states on a quantum computer. And the scenario we have the proof for is if it's an unknown quantum state. So I have to kind of blind myself a little bit and say that this state is coming in, hopefully from a data source. And you might ask, well, what does that full pipeline actually look like? So where does one get quantum data from? And it could be another part of the computation. It could be an analog simulation, like maybe you've heard of these atom traps where people emulate different things and you'd like to transduce the data in. Or it could be an advanced quantum sensor in the future where you can actually do this. And then there's a process that is often termed transduction, which just means move quantum information from one media, like ions, to another one, like superconducting qubits or silicon or something. It's going to go into this buffer where it sits for a second. And then eventually, at least as far as we know today, there's going to need to be some encoding into an error correcting code in what we call quantum memory. But this part will always be essentially unprotected. These sensors are always going to work kind of okay. You might have some ability to manipulate them, but there's going to be a fixed error rate, more or less. And once you have a logical encoding, though, you can pretty much do the operations you want, assuming we're successful in our building of these quantum devices. But because you have this section that's unprotected, it is kind of interesting and meaningful to start asking questions like, well, you did kind of these proofs by hand. They had a little bit of flexibility for different kinds of noise sources, but wouldn't the ultimate test be to do this on a real quantum system where you at least emulate what that noise is going to look like? And so that was our kind of justification for putting it on the quantum device, where we can actually prototype faster under real noise conditions than you can simulate classically once the system gets large enough. You could still technically emulate at these system sizes, but if you blind yourself, you still have these advantages. And so that was what we did. We mapped it to our Sycamore processor that has on the order of 50 qubits on it. And we do these steps where we mimic transduction, which is the state coming in some kind of faulty way, and these joint Bell measurements that just kind of give us classical sketches. And this is a rough layout of our chip where we have some amount of qubits are the gray cosses and some amount of adjustable couplers are these blue pieces. And this is kind of the pattern of how we laid the qubits out, designating system and memory between the two. And so, okay, how well does it work when you run it on these noisy processors? Basically, we trained on noiseless data because, again, we have a formula that could tell us the answer, but we really wanted to see is, could this learn when we didn't know the right answer? Is this good enough to plug into real world data and learn something? And we had some training process where essentially the classical prediction accuracy is fixed by some lower bound based on the amount of information that it has. And our training loss for quantum does quite well. And then this is kind of the big plot for this particular problem, which says, as I increase the system size, so of this state row that's coming in, so this is number of qubits, we're using 2 copies. So when we go up to 20, we're using 40 qubits. We can have this by hand rigorous lower bound that if you've done this number of experiments, that's the best you can do to classify better than some accuracy. We ran the actual classical algorithm to show the separation from the lower bound. And then we compared this to the quantum case where already at system size 20. So this is data from the real device. It's quite noisy and quite hard to get tuned up and running. The number of experiments needed to reach 70% accuracy is often something like 4 orders of magnitude lower. So say if this was a data limited process, even at this small size, there are certain things that you could learn about it that would basically be invisible without this tiny layer of quantum processing. And so you might say, okay, well, that was pretty interesting, but that experiment maybe wasn't so impressive. You used kind of this fixed initial state, did only a handful of gates. What else can you learn about these things? And so I told you that we do a little bit of work on processes. So in this case, we're going to have some unknown process, which just means I have a state. I throw it out into nature. It experiences its reality, you know, its own environment. I bring it back and I ask it questions about what happened over there. And I'm going to have two scenarios, one where it undergoes random unitary evolution, and another where it undergoes kind of a constrained form of this sort of evolution. And this experiment's going to look a lot like the last one. It's going to be kind of the mirror image plus its mirror image. So we prepare some probe state, we expose it to a process, and we take it back. Except now this process is going to be a lot more complicated. Now it's going to be more like, because we have to do these paired measurements and randomizing processes, it's more like the 1300 gate and 40 qubit category, which pushes our noise out quite a bit. So it's a nice experimental stress test of the device as well. And the most interesting part to me was that even unlike before, we're going to pretend like we didn't know there was a right answer. We're actually going to do very basic unsupervised learning. And so our methodology here is that we're going to take these probe quantum systems, we're going to expose them to the environment, take them back, and we're going to contrast this with the conventional scenario where you can do a similar thing, but you're only allowed to sort of use one probe state at a time instead of these joint ones. And these measurements, again, are going to give you out a handful of classical bits that you can just kind of store away. And what I'm going to do is do this about 500 times in one case where I use 2 copies and 1,000 in the other. So I use the same number of total copies, just measure them in pairs or not, take the expected value and variance of each one of these bits. And I'm going to say, well, from a machine learning point of view, now I'm just going to say these are a feature vector for each process. And I'm going to do a little bit more manipulation and say, well, I'm going to compare their similarity with this squared exponential kernel. And I'm just going to stick it in some unsupervised technique like kernel PCA. And now I'm going to take this single copy at a time case. And so here, red and blue are the two things that I would like to distinguish between. And I'm going to give you all this data, and I'm not going to tell you anything about the process. And I'm going to ask, you know, is there anything interesting here? Is there one process? Is there 2 processes? Is there like 100? Should I look any deeper in this problem? And you look at it, and for all intents and purposes, you're like, no, they're all one blob. They're probably all about the same, really. There's probably nothing interesting to see here. And then I'm going to plug in the paired measurements. So these kind of ones that have minimal quantum processing done to them. And immediately they group into 2. And so this is something, an example of, say, I gave you this raw data, and the person doing a little bit of minimal quantum processing immediately saw something that was utterly invisible in the case without it. And so this really gives me hope, at least, that this kind of processing not only doesn't need to know the right answer, but can show us features about our universe that would otherwise be invisible without this kind of minimal processing, assuming that you have some limited ability to collect additional pieces of data for some reason. And so with that, I'll kind of summarize basically, and that the punchline of all of this is that if we could find a suitable data source, even with cloud quantum computing devices today, we seem to be able to learn things that are otherwise totally inaccessible. So recall that there's always these competitions between quantum and classical where people are like, well, I can simulate 50 qubits, and what about approximations to 100 qubits or something like this? But this case is actually a data advantage. So even at 40 qubits, as long as we don't have the ability to sort of tell exactly what the state is coming in, you can get huge advantages over classical, even at 40 or 50 qubits or something like that. And that's the example that we showed you experimentally today. So this work contained, say, things like proofs of advantage in the state learning and process, and sort of experimental demonstrations of this up to 50 qubits. And my hope for the outlook on this work is that it inspires more follow-ups on how to get quantum data sources and sensors. And this is actually a field that's developing fairly rapidly if you've been paying attention to, say, gravitometers and interferometry. Quantum sensors, I think, are on a fast move towards being a very good technology. And we hope to be able to show that this work to people working in that area and say, well, here's a potential additional boost if you could add these features, and are these feasible? How do we interface these with minimal quantum processing devices? And you can ask sort of interesting questions like, are these related to existing physics or interferometry experiments? And how do you go beyond these sort of basic Bell features? And can these proof techniques tell us anything about existing quantum learning? And so with that, I'd just like to thank the people who did most of the hard work in this, like Robert Wong, who did a lot of the theory and proof work and sketching things out, Michael Broughton, that scaled these things up to large scale machine learning, and Brooks and them got together to make sure that we could run on a noisy quantum processor. And of course, all of the co-authors that helped shore up the proofs and the writing and the quantum AI team. And of course, all of you for listening. And so, yeah, with that, I'm happy to take questions or of anything in the talk. We're a more general variety, quantum computing, Alvarez Fellowships, Berkeley Labs, where I'm living in the woods now, or pickling. So yeah, thanks a lot.
Thank you, Jarrod. All right, well, with that, where are we here? There you are. With that, we'll take any questions that you may have. You can just unmute yourself and ask your question if you want.
Okay, so maybe I can start. Jarrod, that was really a nice talk. Thank you. So in some sense, right, like if you think about your chemistry friends that will say, yes, I can make this molecule, or no, I can't make a molecule, right? They are in some way, you know, not on the quantum computing level, but at like the exterior level, sort of involved in using data to help guide models to help, you know, solve physics problems in the same way that like a physicist would say, okay, well, this is my model that I know, and this is the material that I know, and either these match because the parameters are right, or they're completely wrong, right? How do you fold that sort of stuff in, like the classical knowledge that sits in people's brains?
Yeah, so this was the kind of vague references, I guess, or related to the vague references I was making about how data changes the complexities of these problems in a way. And it's because, you go through this chemical education, you learn how to synthesize certain systems, you see things in nature, and you're collecting these models over time that I would, I guess, term close to one of these limited models of advice, where you've now seen examples, and that, maybe a computation of something's free energy might not be so informative, but this type of nitrogen, being adjacent to this type of carbon exists everywhere, and so I can probably make it. Or like this one I've never seen anywhere, and I know all these kind of side reactions happen, so it's probably not possible. And so they're implicitly using this expertise, and how to codify that in like a computational framework. It's actually interesting. We hadn't seen so much before on, I think, maybe it's because if the knowledge is strictly classical, it sits in the same complexity class, but by leaning on nature being quantum, we can separate. But I think there's a even practical separation where, say, if gaining that knowledge, cost you n to the 100 power, it's still polynomial, but you still cared that you were a lot faster in practice and identifying things.
Yeah, or, gaining that knowledge, like we've already gained it, right? It sits in your head in the chemistry side, right? Like, can we use that?
Yeah, exactly. And the universe has already done some amount of simulation on Earth showing us which things like to be made. And we're taking advantage of all that, few billion years of pre-processing time to boost ourselves. Even if it's, finite time, it's still very helpful. Yeah, good question. Good question.
Hey, Jarrod. Nice talk. I have a question. So we know that in classical machine learning, there's an enormous gap between theory and practice. Do you think that for quantum machine learning, the gap is somewhat smaller or bigger?
Yeah, it's a good question. I think, yeah, so it kind of depends on the sectors of machine learning that you're in. So that people paint a lot of things now as quantum machine learning. And for this particular case where you have entirely classical inputs that are, say, well geared towards specifying your problems, and entirely classical outputs, so this might be like image recognition, there's very little theoretical promise that we should ever be much better at that. And you might ask, well, once we can actually build the networks, empirically, you might not have guessed that deep neural networks were any better classically for this task than other things. Is there some big gap between quantum and classical? And I think part of the problem is we lack not only a proof that it would be better, but we lack any kind of intuition as to what features a quantum device would use for like a classical image to help us. And so I think we need a little bit more work there to even build the primitives that would go into a network that says takes MNIST data and classifies it. And if we could come up with some way in which, say, I don't know, edge detection or wavelets or something had a natural compact quantum description, then I'd have a little more hope. But I'm a little worried there's probably not a huge empirical or theoretical gap there. I mean, it'd be great if there was, but on the other hand, if you're processing quantum data directly, I think there is probably actually, we can do a lot better than even we've written down by hand already. Just you're processing the data on its natural footing. And if you're comparing to conventional experiments, I think perhaps there's a lot we can learn.
Yeah, so what I'm thinking is really that in the classical world, the experiments are way ahead of theory, right? And in quantum, it seems like the theory so far, plays a pretty important role. But does that mean that that's solely because the experiments we can do is they're very limited, or?
Yeah, I mean, I think at the moment it's because the experiments we can do are somewhat limited. I mean, we're hurt so badly by noise at the moment that even when we have 100 qubits, it's very hard to go try to compete against a classical model for doing these things. But I would say it's also that right now, we even have quantum models that are very biased towards experimental convenience. And what I mean by that is, we write down things in terms of 1 and 2 qubit gates because that's what's easy to engineer and things like that. But the movement from that to like a reasonable encoding of, say, an image, it's a bit tortured. And so if you look at what works very well in machine learning, the easiest thing is if you've engineered a feature that has an obvious, basically linear relationship between input and output. The further you get from that, the more work you have to do to fitting the square peg in the round hole. But we're starting from like bitwise manipulations and hoping to learn things that classical networks already do. And I think that might be a little too much of a jump. We might need bigger quantum primitives, like, something that takes in full images, but that's quite hard experimentally. And so I think that's been a limitation too, that biases us towards things that are good for experiment, but not good for the data we're trying to ram into it. And we might need a little more progress till we can line the two up.
Thanks.
Thank you for the questions. I would have one last question that maybe goes a little bit in the same direction, which is, so you talk about that you need fewer data for training when you use your quantum approach. Is it more prone to bringing bias into the whole analysis chain?
I guess it would depend a lot on where the bias is coming from. So for our contrived scenarios, it kind of reduces it because we have uneven, we have kind of even sampling of our training data set and things like that. And so we're kind of getting more accurate overall, apart from slight experimental imperfections that you might accidentally learn the wrong feature or something like that. More generally, I think it's a very hot topic right now to talk about, even from both a beneficial and a negative side. Like, once you choose a model, inevitably in high dimensions, you're going to extrapolate rather than interpolate. And a particular model, even if it does the same on a training data set, will have some kind of bias towards what it thinks generalization should look like. And so if you're using very, very few data points, you're probably more attached to whatever the inductive bias of your model is than one you might be able to average out at higher data points. But sometimes this is good. Like, if I'm using a quantum model for a quantum system, a hope might be it has a better inductive bias towards the true generalization set. But if, say, you're using it on a mismatch and you're training the same, you might end up with a bias that's worse, basically. And so I think it's a interesting and important question, like one we sometimes take for granted, that, say, convolutional networks bake in either by hand construction a lot of structure that images we think have. And this is good in many cases, but there can be other hidden biases in your system if you dramatically reduce the data and simply match your training set. So yeah, I think it's a good question, and one we don't understand so well yet on quantum models. I think we're still trying to understand what biases they have. In particular, we often build them unitarily, which, with enough ancilla qubits, you can make that computation look how you want, but naturally they're reversible, which might not always match a learning problem. So that could introduce a small bias to your problem you didn't expect.
Interesting. Okay, thank you. With that, we're on top of the hour. I want to thank Jarrod again for taking the time out to give us this wonderful overview of his work. And we will see each other again in about 2 weeks, in exactly, 2 weeks minus 1 hour. And then Lex is gonna tell us something about quantum computing meets condensed matter physics. Looking forward to see you guys there. And then, and with that, thanks again.